Hey Geometry, welcome to section 7.6. We're going to focus on similarity transformation, namely dilation in this section. So a dilation is a transformation that enlarges or reduces the original figure proportionally. Since a dilation produces a similar figure, a dilation is a type of similarity transformation. So this is unlike our congruence transformations, which were like translation, reflection, rotation. Those keep figures congruent as they go through those. Dilation keeps things similar. So the angle's the same, the side's proportional. Dilations are performed with respect to a fixed point called the center of dilation. And the scale factor of dilation describes the extent of the dilation. The scale factor is the ratio of a length on the image to the corresponding length on the pre-image. So the pre-image, if you go back to our transformations, the pre-image where we start from, the image is where we end up. So a dilation with a scale factor greater than 1 produces an enlargement. That should say of an image that is larger than the original figure. So that's if our scale factor is greater than 1. A dilation with a scale factor between 0 and 1 produces a reduction. An image that is smaller than our original figure, or pre-image. So for example, FGH is dilated by a scale factor of 3. And so since that scale factor is 3 is greater than 1, this is an enlargement. So all the lengths from one triangle to the next are going to be 3 times as much in this case. And also these distance here, this is going to be like from C to H. C to T is going to be 3 times as much, and C to F, C to R is going to be 3 times as much. And so then in this case, ABCD is dilated by a scale factor of, this was actually 1/4, and so this is a reduction. All of those lengths get cut by, divided by 4, or multiplied by 1/4. Determine whether the dilation from A to B is an enlargement or reduction, then find the scale factor of the dilation. So in this case, we're going from A to B, and so you should be able to just kind of see A is the bigger figure going down to B. This is a reduction, but then we want to figure out the scale factor. So what do I multiply to get from A to B? And so this length, you pick any length if they are actually similar, which these ones should be if it is a dilation. You can pick any length. I could do this length here as 4 down to 2. And so you can think about like 4 times our scale factor. A lot of times for scale factor, we'll use like K. 4 times K equals 2. And so you could solve for what your scale factor is. You might just be able to realize it. 2 over 4 is 1/2. You might realize, yeah, we shrunk by 1/2 for that reduction. That's just one measurement. We could have done this bottom, which is 6 across to 3, going from 6 to 3. This angle, that'd be a little trickier, right? We have the hypotenuse of these 2 right triangles. So whatever that is, this length should be, or whatever that original length is out here on A, hypotenuse, B is going to be the same. And then we can also measure like distances from wherever they're dilating to, if we can figure that much out. So in this case, we are dilating toward the origin. And so this distance here would be the double that one. So we cut it in half. All right, in this case, going from A to B, that is an enlargement. And so we know that, for instance, A's side here goes from 1 to 3, so our scale factor, or K we could call it, is 3. All right, and I guess I should have said that over here. That's our scale factor. Because K was not specifically defined. Scale factor. Could have done that on that side. We could have gone from 2 to 6. Realize that's 3 times as much. You know, this is up 1 over 1, up 3 over 3. There's several ways we could do that. That is, that center of dilation is the origin in that one as well. All right, so example 2, Mariano wants to enlarge a picture he took that is 4 inches by 7.5 inches. He wants it to fit perfectly into a frame that is 400% of the original size. What will be the dimensions of the enlarged photo? So 400% is our scale factor. 400% is just going to be times 4, right? That's 4% is per 100, so 400 per 100 is just a scale factor of 4. So our dimensions are going to be 4 times 4 and 7.5 times 4. So 4 times 4, we get 16. 7.5 times 4, we'll get 32. No, 30. Sorry. 7.5 times 4 is 30. And so that would be a 16 by 30. 16 by 30 for that image. All right, third example, graph the original figure and its dilated image, then verify that the dilation is a similarity transformation. So our original figure here, I'll go ahead and pause and put some points in. All right, so I've got the points on there. And so our original pre-image is this outer triangle to that smaller image as our inner triangle. And so we know that it's a reduction. We're going to ultimately verify that this is a dilation and a similarity transformation. What is the scale factor here? We're going from OM to GD, and so our scale factor ends up being our image over our original. So this length ends up being, if we look at GD, that length is 3 over, and then this length here, OM, is 6 plus 3 is 9, 3/9, right? And that's GD over OM. And so our scale factor here is 1/3. And so let's verify that that's the case for all of them, right? This reduced to 1/3, and so that's our scale factor. This little triangle is 1/3 of our original triangle. So then our next one we could do, our easier one, is DF over MN. Is that also 1/3? And I could write this all in the same line if we wanted. And so DF is 4 across, and then MN is 12 across. 4/12 reduces to 1/3. And that one's not too bad. The last one we want to do is GF over ON. And that one's a little bit trickier. So let me go over here. GF is this little hypotenuse. So effectively we can use those sides that we already figured out that this is 3 across and that was 4. So we can do 3 squared plus 4 squared equals GF squared, and then we take the square root. And so this one works out to be pretty nice. 3 squared is 9 plus 16 is 25. Square root of 25 is 5. That is a 3, 4, 5 triangle. We should kind of recognize that right away as that Pythagorean triple. So GF is 5, and so we might think of what we need the other thing to be, ON, but let's just double check and make sure it is what we expect. ON horizontally, we're going 12 squared plus 9 squared. So 12 this way, 9, you could have gone 9 then 12, and then taking the square root. And so that is 144 plus 81. Make sure I've got that right. That is the nice 144 plus 81 is 225. So it's the square root of 225, which is the nice 15. So yes, we do end up with that 5 over 15, and that does reduce to 1/3. So all 3 sides are proportional. So that side proportional to that side, that side's proportional to that side, and then the hypotenuse side's proportional to that one. All right, one more. You can go ahead and try this one yourself first. I'll go ahead and get some points down. All right, so got the points graphed on this one. Our original is the smaller GHIJ. GHIJ appears to be a rectangle. And then our image, that's our pre-image to our image, is the QRST, this larger red one that I've drawn. And so it's getting larger, so this is an enlargement. And so we want to see, what is happening here. So maybe I'll start on the left side and realize that, QS over GI, what is that ratio between those sides? And so that length, QS is 2 over GI is 1, is a 2. And so our scale factor here from the little one to the big one is 2. And so let's verify that for all of our sides. So QR across the top, QR over GH is 4 over 2, which is 2. RT over IHJ is 2 over 1. So 2 is that vertical distance, 1's that vertical distance. And then finally ST over IJ is another 4 over 2. And so all these you end up getting 2. They all have the same ratio. Technically, actually, with that works with triangles to show all the sides are proportional. Technically, with quadrilaterals, we should go just a bit further to show that some angles are congruent as well. And these all end up being perpendicular, and we do have all 90-degree angles. We could go through and show that, but we'll skip that one for now. All right, and then final example on the back here, example 4, quadrilateral JKLM has vertices at those points. Graph the image after a dilation centered at the origin with a scale factor of 2.5. So we're going to go going 2.5 times the distances. So let me start with my pre-image, and I'll get that drawn up. All right, got this one drawn up. And so this is our quadrilateral JKLM, and we are going to be using our origin as our center of dilation. And so what we're going to be doing is basically doubling, actually more than doubling, 2.5 times all those distances. So for instance, if I focus on J first, if we go to J, I realize, all right, that's 4 up. And if I go 2.5 times that, so you could do it in your calculator. 4 times 2.5. I'm going to go 10 up. So it's another 4 and then half that, so 2 more. So that gets us up to 10. That's just vertically how far I'm going. Also 2 to the left. If I go 2.5 times that, so that's going to be 4, 5. So at 10, -5. All right, so if I'm like -2, and you could even take the -2 times 2.5. And so we're going to end up at -5 for that x coordinate and the y coordinate. So that will be J, and we can do a little prime to show that that is the image. Then we'll do the same thing for K. We're going 2.5 times that distance, so 4, 5 for K prime. Sorry, I put that point in the wrong spot. I forgot to do the horizontal distance. So we're also going, that's 2 to the left from this point. So we're going double that, and then another half, 4, 5. So we're going to actually end up at -5, 5 for K prime. L is 4 to the left, so that's going to be 8, 9, 10 to the left. And then it's also 2 up, so that's going to be 4, 5 up. So 8 to the left, 5 up is where L ends up, L prime. So we've got kind of the top part of this quadrilateral that's being multiplied by 2.5. And then M is 4 left. So that's going to be another 4.5 of that, so 2 more, so -10. And then it's 2 down, so no more 2 more, and then another half, so 5 down. So -10, -5 will be where M prime ends up, and that'll finish off our dilated quadrilateral. All right, similar practice. You can go ahead and try these first. All right, so this one, we're going scale factor of 1/3. Got our original figure drawn, and then essentially all those dimensions are going to get multiplied by 1/3, and we are still centered at the origin, so we're kind of going straight toward that point. So for instance, this Q is 6 up. We're going 1/3 that distance. That'll put us at 2 for Q prime. This r is 6 left, so now it's going to be 2 left, but it's 3 down, and so the third of that would be 1 down. So 2 left, 1 down would be r prime. And then similar thing over here, 6 right, 3 down, so a third of 6 is 2 right, a third of 3 down is 1 down, so 2 right, 1 down is where S prime is going to end up. And so there's our little dilated, reduced image there. And one more. All right, this last one is a bit weird. We got a scale factor of -3. So effectively, we're seeing with this. We didn't really cover this, but in what the dilations, what the scale factor actually means, whether it's enlarging or reducing. Negative effectively gives us a point symmetry. We go through. We were focused on the origin here, and then it also, if it's below -1, it's enlarging after it's kind of reflecting through the origin, as well as if it's between 0 and -1, it can reduce while kind of reflecting through the origin through a point. So I'll start with A. It's 2 to the right and 1 up, right? So that's 2, 1 is that coordinate. I haven't been writing that much, but I'll write that. Effectively, when we're going from the origin, this is kind of nice. We can just basically multiply each by -3. We're 2 to the right, and so we're going to go the opposite of that direction 3 times as much. So 2 times -3 gives us -6, and then 1 times -3 gives us -3. So x coordinate is -6, -3, and that's actually where A prime will end up. All right, and then we can do the same with B. It's 3 up, and so we're going to go the opposite direction. Instead of 3 down, we're going 3 times that much, so we're going to go 9 down, and that's where B prime ends up. And then C, we're left 1, 2 up, so instead of left 1, we're going to go right 3 times that, so 3, and then instead of 2 up, we're going 6 down, so right 3, 6 down. That's where C prime is going to end up. And then finally, D is just 1 up, and so we're going to end up 3 down from that center of our dilation. And so this thing kind of, let me get it drawn in here. We should see it kind of reflected through the origin, but also got scaled up in that process. So this was kind of a weird enlargement and reflection through the origin. It also can kind of appear like a rotation when that happens.